when we're talking about fundamental forces here, there are pretty much four fundamental forces that we see in our everyday lives that we really care about. And the first of these forces is gravity. Okay, you fall down the stairs, you toss an egg off the roof, you try to figure out gravity in a video game, whatever. But gravity takes place whenever two objects have mass. So there's some intrinsic stuff making up this object. Okay, and because objects have mass, they will experience a gravitational attraction towards one another, and gravity will only ever attract. So if you have a soccer ball in the earth, you drop the soccer ball, it falls towards the earth. But one of the interesting things about gravity and these forces is that they're acting on both of the objects. So while the ball is falling down, the earth is actually also like falling up, or it's falling towards the ball. It's not moving nearly as much because the earth is ginormous, right? It's much more massive than the soccer ball, but technically the soccer ball is pulling it. Okay, and technically, like, you're sitting at home and I'm sitting at home right now, but technically we are pulling on each other because, I'm made up of mass and you're made up of mass. And, this calculator is made up of mass, so I'm technically pulling it. It's just that in order for a gravitational force to become large, you need a lot of mass. Okay, you need a lot of mass to get gravity to really start going. But it is there for everything. And it's infinite, so kind of a neat thing. Now, gravity is holding together our solar system. The sun has a ton of gravity. It's a very massive object. It's 2 times 10 to the 30th kilograms. And it keeps the planets in their orbits due to gravity. If you had a slice of pumpkin pie left over from Thanksgiving, and you were just sitting out here in space, you could eat it easily just by keeping your mouth open. You'd have to wait a while, but you'd be pulled to the pie, and the pie would be pulled to you, and then you could just go hop, 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 and you would eat all the pie. Which, I love pumpkin pie. Actually, I love whipped cream, so whatever. But that's gravity, okay? Objects have mass, they attract one another. Pretty straightforward. Now, another type of force that we have is an electric force. If an object has an electric charge, then they can attract or repel other objects with electric charges. And you talked about this last year in chemistry. You've got like protons and electrons. Protons are positively charged, electrons are negatively charged. And if you have these positive and negative charges here, you're going to get these attractions and these repels. We know that like charges repel, so if we have 2 negative charges or like 2 electrons, they're going to repel one another. We know protons, since they are the same positives will repel one another. Once again, they're like charges. But if we've got opposites, they will attract one another, which is a kind of neat thing about electric charges. We can not only attract like gravity, but we can also repel, which is really cool. Now, pretty much every everyday force that you feel is actually an electric or electromagnetic force, okay? And what I mean by that is like touch something, okay? Like physically, like touch a wall or touch your desk or like touch your chair or lean back or touch your hair. Anytime you touch something, this is an electromagnetic force. Except, are you really touching anything? Here's a button, okay? I've got this like lit up keyboard here. There's a million buttons on it. And every time I push a button, let's see what actually happens. When I push a button, if we zoom in on this, there's my finger, artfully drawn as seen. But my finger's made up of like molecules, right? It's got all sorts of like carbon and skin protein fibers and whatnot. And if I continue to zoom in on that, it's really just made up of protons, electrons, and neutrons in the nucleus. So if I actually think about this, I have a bunch of protons and electrons in my finger, and there's a bunch of protons and electrons on the button. And what's going to happen here, if we really think about it, is all of the negative charges here in the electron clouds are going to interact with all of the negative electrons on my fingertips, because there's an electron cloud there. And these are like charges. So what are they going to do? They're going to repel. So whenever you push on something, you're not actually touching it. These Electrons are just becoming close enough together to experience a force acting on them. And our human bodies are just set up so that when you feel a force, your neurons detect the force and they input it into your brain as a touch so that you don't accidentally spear your hand on a sharp object. Okay? So you're never, ever touching anything. In order to actually touch something, in order to bring an electron into an electron, you would need an insane amount of force to do that. So yeah, you're not touching anything ever. You're just kind of floating on stuff, which is kind of weird. This also means if you were to, like, you're sitting in a chair right now, but you could, in theory, if your chair's got a bunch of electrons like this, and your butt has a bunch of electrons like this, there is a possibility that these electrons don't overlap, and you get something where all of your electrons and the chair electrons miss, and you fall through your chair. Except that's statistically very improbable to happen, but technically it could. You could fall through your chair. Except the odds of that are 1 in blah, 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 forever, right? So you're never going to have that happen. But it could. But it won't. So yeah, you're never actually touching anything. Kind of neat with electromagnetism. Here's a more zoomed in picture of kind of what you talked about in chemistry last year, of your nucleus with your protons and neutrons, and then those electrons going outside. I just want to clarify something though. Whenever we talk about the electron, it is often drawn as the electrons going in these orbits here, but remember, the electron isn't going in orbits. It's actually going in a cloud. It just exists. These are your s, p, d, and f orbitals. These are your spheres, and then you've got a stupid figure 8, and then you've got this weird looking thing, and you've got a figure 8 with a weird spiky thing on them. I'm talking about from last year. Looks like something like that. This is actually what the electrons are doing. They're just existing randomly in there. They're not moving in circles. Okay, but we do have other fundamental forces that can occur if we start looking deep within these nuclei themselves. So if we look within the nucleus with neutrons, neutral charges, they've got no positive, no negatives, and then the proton, which we know are positively charged, we can see that we have a strong nuclear force. Yeah, what's up, Laura? Neat. So we have this strong nuclear force actually holding the proton and neutrons together in the center here, because we know that a positive and a negative charge are going to pull one another, but why is a positive and a nothing charge going to hold together? What the heck's going on there? So this is actually the strong nuclear force that's holding these nuclei together, the neutron and the proton. Otherwise, they would have no reason to be next to each other. And the way the strong nuclear force actually works is there is a particle known as a gluon that is actually being passed between these, and it's binding them together. And the reason that gluon exists is because the protons and neutrons are actually made up of smaller particles. These are not actually the smallest thing that can exist here. You can get smaller than protons and neutrons. You can have something known as a quark, and these quarks will actually be passing these particles back and forth, which allow the strong nuclear force. So that's what's holding the actual neutrons to the protons to make up a nucleus, which is kind of a weird thing. Now, if you have a large enough nucleus, and you probably didn't talk about this last year in chemistry, because chemistry's only kind of dealing with, well, whenever you took chemistry last year as a sophomore, you're pretty much only dealing with basic reactions. But if you have a large enough element, something I don't know, uranium-238, these nucleus become so large that the strong force can't actually hold them together. The strong force is actually very small. The force from that strong force actually is very strong until you get to some point. Once you hit a point here, if here's my nucleus, once I go out so far into a radius, my strong force dies off. Its arms aren't long enough to hold everything together, right? It's like, oh, I can't reach it, and then it just loses it. So what happens is when these nuclei get so big, the strong force can't hold it together, and then since you had a positive on the inside with all the protons, and you had all those electrons in their clouds out here, the positive and negatives actually rip the nucleus apart once you get to a certain point. And what occurs with these radioactive decays is that if you should be holding together, if the strong force should be strong enough to hold that nucleus together, it's like, yeah, my arms are big enough, I got this. Sometimes they decay anyways. And this occurs due to a weak nuclear force. Basically, all the weak nuclear force is that as the strong force is holding the nucleus together, the weak force just comes along and is like, whack, ah! And then all of a sudden you have a radioactive decay occurring. So it's kind of weird. It's kind of a force that exists because it has to exist in order to get these decays here. Even though the decay shouldn't be happening, according to the strong force, it does anyways. And that means that there's another force that needs to tie in and to cause that. So kind of a weird thing there, but kind of neat as well. Okay? So that's what we can see with the weak nuclear forces. And that gives us 4 forces there. We've got gravity, we've got electromagnetism, we've got the strong nuclear force, and the weak nuclear force. We got 4 forces, okay? But if we were to rank these in order from the strongest up here to the weakest down here, we might not actually get an order you'd be thinking of. If we were to rank them, we would actually see that the strong nuclear force is the strongest. I mean, it makes sense. It's got the word strong in the name. The next strongest force, though, is actually the electromagnetic force. And then it's the weak nuclear force, followed by the gravity or the gravitational force. Gravity is actually super duper weak. You can break gravity all the time. Like, you can stand at home and you can jump up and down. And for a brief moment, you have defeated gravity. Congratulations. You've never just been sitting there and been like, hey, watch me rip off my arm. Like, 1, that would hurt a lot. But 2, there's a lot of contact forces at play there. There's a lot of electromagnetic. You've never just been like, yeah, watch me karate chop this nucleus in half. What? Actually, when you do that, you get an atomic bomb. Yeah, so gravitational force is actually super duper 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 weak. Okay? The strong force is extremely strong, holding those nucleus together. The electromagnetic comes next, then the weak, and then gravitational. Now, for each of these strong nuclear forces, like I said, and for each of our other forces, we'll be talking about specific things, their carrier particles and properties. For the strong nuclear force, the carrier is the gluon. Remember, I told you that a proton is actually made up of smaller things. It's made up of quarks, and quarks can have, there's actually 6 types of quarks, but the ones we are concerning about are up and down quarks. Up quarks have charges of plus 1/3, and down quarks have charges of minus 1/3. So if you wanted to make a proton, which is a charge of +1, you would need a, whoops, I did right, this is 1, I meant this is a 2/3. You would need an up, down quark to do that, because you're going to have 2/3 plus 2/3 minus 1/3. That's going to equal 3/3, which equals +1. So that gives you a proton. If you want a neutron, you want up, down, down, because that's going to be 2/3 minus 1/3 minus 1/3, which gives you 0. So there's no charge on the neutron, which makes sense. The electron, you might think that it would be down, down, down. But the electron isn't in the nucleus. The electron doesn't have these gluon particles, and that means the electron is not made up of quarks. The electron is the smallest thing that makes itself up. What is the electron made out of? It is made of electron. That's it. It just exists. That's it. It's done. So while the protons in the nucleus and the neutrons in the nucleus are made up of these quarks, which are smaller, and these quarks have gluon properties, the electron is just an electron. And The property we care about is called color, which is a little weird. And we know that these hold the protons and neutrons together in the nucleus, as well as holding the quarks together in the protons and neutrons. So that's what we see with our strong nuclear force as one of our 4 fundamental forces. If we take a look at electromagnetic, the carrier particle for the EM force, which is commonly called, is a photon. So a beam of light is a photon. So photons carry electromagnetic forces. The property is an electric charge. Those are pluses and minuses. We've talked about those in the past. And the 3 things we see from them, we see static or current electricity. So static electricity is something I experience every morning. When I wear my bathrobe, it kind of charges me up, and then when I touch a bedpost or something, I get shocked. Maybe you did this as a kid, or maybe you did this yesterday. If you've got carpet in your house, you put your socks on, and then you kind of like scurry around the floor. And when you do that, you build up an electric charge. And when you touch someone, you'll zap them. We also see current electricity. That's just all your electricity running through the walls of your house. It's what you're using in order to use your computers to watch this stream. It's pretty much everywhere. It is fundamental to the modern way of life, electricity. We also see it in magnetism. So electromagnetic is electromagnetism. So we actually see this with magnets as well. And all the contact or the touching forces, I'm not really touching you because you can't touch anything. They're just forces interacting. So kind of a neat thing there. For the weak nuclear force, the carrier is actually a little weird here. It is the W plus, W minus, or Z naught particles. Don't really worry about what those are. Particle physics is kind of weird. But the property behind them is flavor. We've already done color, so why not flavor? And these are only involved in radioactive decays. So that's what's going on there. Technically, this is a property of kind of like quark values there. Okay. And last but not least is gravitational, my personal favorite force. Coming from the world of astronomy and astrophysics, we did a lot of stuff with gravitational forces. We know the carrier of it is the graviton. We know the property is mass, and we haven't really seen the graviton yet. Some people call it like the God particle. We're starting to get more information about it at the Large Hadron Collider in CERN. But its property is mass that we care about. And the 3 things we see from it are weight. So whenever you step on a scale, you can blame mass for your weight and the graviton for that. Falling objects, so anytime we get something that's falling, we can blame gravity once again. And planetary motion is actually due to gravity. Okay? And planetary motion is actually just falling, but it's falling with style. So that's another thing we see there. Okay, so those are our 4 fundamental forces and everything that goes kind of into them. But I guess the real question at this point becomes, why do we only have 4 fundamental forces? Why not 5, 6, 7, 8, 9, 10, 38, 42, 79? Like, why only 4? Well, we actually did start at one point in time with more. At one point in time, electricity and magnetism were different things. You could have charges and you could have magnets, like north and south poles, right? You stick them on your refrigerator. So they were different things for a very long time. And then it wasn't until James Clerk Maxwell came along that electromagnetism, we found a relationship between electricity and magnetism, and we combined them together. So that was one unification of 2 forces into one thing. We did the same thing with planetary motion and falling objects. For a while, it was believed that planetary motion was different than gravity. How could gravity, influence the planets moving around? Beyond that, we didn't understand a lot about planetary motion for a very long time. For a while, we had a geocentric model of the solar system, which is that the Earth is in the center and the sun moves around us, and that doesn't make any sense now. But at the time, it did. So it wasn't until Newton came along and he kind of showed that you can have falling objects due to gravity, and this same gravitational pull, this attraction between masses, will also keep objects in a planetary motion. We didn't have a really good idea at that point in time. It was actually, hypothesized for a second that maybe the planets are held around the sun due to a very large spring. except nobody's ever found this spring yet. Well, the spring idea works with like mathematically, but the fact that there's not a giant spring connecting us to the sun is an issue. So gravity ended up being both of those features, one for planetary motion and one for falling objects. So we combine them. We've actually combined a lot more things from that. If all forces are just forces, they're just pushes and pulls, then why do they need to be different at all? Why isn't there just like one force? We've already seen electricity and magnetism combined. We've seen planetary motion and falling objects combined into gravity. Why don't we just combine everything and just call it force? So we actually have combined electromagnetism and the weak nuclear force. We call this the electroweak force. And we've actually combined the electroweak force with the strong nuclear force, and we call this the GUT, the Grand Unified Theory. We actually have good mathematics set up for that. We're not going to talk about them in class because they're crazy. They're very, very complicated. But we've done that. Like in the world of science, we as a community have come together. We've combined pretty much every force except one. We have not yet combined gravitation and the Grand Unified Theory. This world of gravitational forces are like really, really weird. But if we could combine them, and we're working on it, we will get a super unified theory. Sometimes you hear this called like string theory or like the bubble theories. You'll hear it called a whole bunch of different things, but it's basically trying to take all of the forces that we know about and bring them into one. And gravity is really the sticking point here. This has been looked into by Einstein, Stephen Hawking. Some of the greatest minds of our time have tried to get further and further on this, but it is a very like weird topic because if you want to talk about the graviton and how it's pulling objects together, then you need to go onto a fundamental level of what is actually making up objects. What is giving these objects their stuff, their existence, their mass. If you want to get onto that very, very small level, well, now you're also dealing with the strong and weak and electromagnetic forces. So we haven't had a really easy time of looking at the gravitational force at the small level yet. And how do I combine it with all these things to get a super unified theory? It's very complicated and difficult. But the world of science is working on it. We're trying our best right now. Maybe we'll get it in our lifetime. Who knows? In the end, though, all forces are just forces. Just like steam, water, and ice are all the same thing. They're all H2O. Forces are forces. A force is a force, of course. So if you've got gravitational force, you could have a weak nuclear force. You can have electromagnetic force. You can have a strong nuclear force. They're all just forces. So throughout this unit, when we talk about a force, all we are talking about is a push or a pull of something. That's all we're talking about. Okay? It doesn't matter where that push or pull is coming from. That's what is going on there when we talk about a force. It is a push or a pull between two objects. Okay? And that's it. That's the basic rundown of forces. If you wanted to, and this is in the PowerPoint, or I could just leave this here, this is kind of some of the weirder things in terms of breaking down stuff. The various strengths of objects at different distances, the weak interaction, the mass, energy, flavor, electric charge, and color charge, quarks, gluons, the different particles that mediate this, what the particles would kind of be, their different mass values. We don't need that for this class, but if you want it, it's here. Okay. So yeah, that basically takes us out through the world of forces for right now.